I'm here today to talk to you about non-revenue water reduction. This actually is a topic which is not taught in most colleges, engineering colleges or non-engineering colleges. But it is a field which has been growing for the past 15-20 years because this NRW reduction is what is going to get us the water to feed the population, growing world population in future. Because you will be aware of the climate change, the glaciers melting, the fresh water depleting. I'm not going to go through those numbers again because they are available in numerous websites. But we all know there is a water crisis which is coming. And just this is a chart which I will refer to again and again. I will keep coming back to this chart. Why? I'll tell you later. Let's see a few numbers first. This is an estimate. Okay, I'll have to read these numbers out. This is an estimate of these are estimates which depict how serious the NRW problem is today. $18 billion worth of water each year is considered to be NRW. These are World Bank numbers. More than 32 billion cubic meters of potable water leaks out from the water systems worldwide. If we can save this water, and given the water supply per capita rate of 135 LPCD, which is prescribed by the manual published by the CPHEO, we can feed 230 million people. And only 10% of the leaks are visible. The rest 90% keep leaking, and we have no idea that this water is leaking. Unless a utility does a water audit, they will never know how much water they are losing. These are the real and apparent loss numbers and the NRW in billion cubic meter per year for developed countries, for Eurasia and developing countries. As you can see, the developing countries have a very serious problem. This 26.7 billion cubic meter per year. Why is this serious? First of all, because developing countries, most of them have a water crisis. Secondly, they can't afford to lose this kind of water because they're spending billions and millions in treating that water and supplying it to the consumers. So it's not only a water loss, it is revenue loss for utilities who can't afford it really, because most of the utilities, they don't have money. Okay, let's come back to this chart. This chart is a standardized format published by IWA, International Water Association. They are the pioneers in NRW reduction and water loss studies. Prior to this chart, there were many terms which were being used, like unaccounted for water, technical losses, commercial losses, financial losses. There were no standardized definitions. Then IWA came up with this chart. This chart is now clearly defining NRW, non-revenue water. There is nothing like a UFW, or people at least don't prefer to use UFW, because unaccounted for water means there is some water which you don't know where it's going. And that should not be the case. Even if it's getting lost in the system, you should know how much water is getting lost in the system. So the experts worldwide now prefer to use non-revenue water. And how is non-revenue water estimated? Very simply put, it's the water which the utility puts into its system and the water for which it gets revenue, the balance is non-revenue water. It has many components, and we'll go into these components in detail when we are seeing the subsequent slides in which deal with how to carry out a water audit. these are the components of apparent losses. Now, okay, let's go back to that chart. Water losses are basically of two types, real losses and apparent losses. Now, what are real losses? Real losses are nothing but leakages. Those leakages can be from the treatment plants, from the reservoirs, from pipes, from walls, from service connections, and even after the service connection. But that is the water which is really being lost from the system, physically being lost from the system. What are apparent losses? Apparent losses are those where the water is being supplied to the consumer. It's being used for one purpose or the other, but it's not fetching the utility, the revenue that it should. So that's not a physical loss of water. That is rather a loss of revenue. And what are the components of the apparent losses? How do they occur? Non-revenue water is going to be measured by a meter, which is meter or meters, which measure the input of a system, right? Look, I'm going to be assuming that you know a lot of things. If you don't, please feel free to ask questions, right? Because I do not know what your course content is or will be and how much you really know. So if you people really at any point of time think that you want to ask questions, please go ahead, okay? We won't reserve questions for the end of the presentation only. Fine, so to measure NRW, the basic two things which are required are to measure the input to a system, which is measured by what we call bulk meters. And at the other end, you have to measure the consumption, right, by the bulk consumers and by the domestic consumers, by industrial consumers. These are the two things which will measure your NRW. These are instruments basically. They will have built-in accuracies. We have electromagnetic meters which are mostly used for measuring the input, the bulk inputs. They have accuracy up to 0.5% under test conditions. Under field conditions, it's not always 0.5%. It can be more, but this is the minimum error which will be there in your meter. So whatever NRW number you're quoting, that 0.5% error is always there. So that is regarding the bulk meter, right? Similarly with consumer meters, the consumer meters come with a certain graph. If they're not sized properly or anything other than, if they're old, if they're not calibrated properly, there will be errors in that number also. So this is not actually water which was lost from the system. It is an apparent loss. Okay. Billing and accounting errors. You really wouldn't believe the kind of mess the billing system is of utilities, because we have meter readers who go knock on a door. If the door is not open, they will enter what is called a standard tariff, right? So, and even if they read the meter, they make many errors. So this accounts for a lot of NRW, the apparent losses, at least in developing countries. In developing countries, when the water audit is started, in the beginning we get an NRW number, and we generally presume that it's split half and half between real losses and apparent losses. So if the NRW is 50%, we can say it's 25% real loss and 25% apparent loss. That's the assumption we start with. Then of course it's checked back. Unauthorized consumption. I don't need to tell people living in Delhi what unauthorized consumption is, right? This problem was solved in the power sector when it was privatized. but it's rampant, it's simply rampant in the water sector right now. Let's talk some more about meter inaccuracies. How do meter inaccuracies creep in? There is a particular use for every type of meter. For bulk meters, as I said, the electromagmeters are the best in the market for a given price today. But even these meters have this graph. If you see, the x-axis is the velocity and the y-axis is the error. For velocity through the meter between 0 and 1 meters per second, the error increases exponentially. So the meter has to be sized correctly. If you're not sizing your meter correctly, then the error can be as high as 2.55% in the bulk meter itself. And this is very, very important because this error is going to be carried forward into your entire system. Right? So it's going to affect the NRW of any DMA, any zone, any part of the system for which you calculate the NRW. Defective meters, meters which are not maintained properly. Calibration of a bulk meter should be carried out at least annually. If it's not done, the errors will creep in. The meters have a life, a useful shelf life, after which there is no guarantee for the inaccuracy. They won't be following this curve. So after the useful life of meter is over, they should be replaced. Accounting errors, billing errors. As I said, some when the meter reader goes and knocks on a door, if the customer is not there, he will not read the meter. He will simply move forward. Just to well, not to take the name of the utility, but they started an internal NRW measurement program, and they came up with very interesting numbers where the NRW was varying from 75% to it was negative. So why was that? Because they were taking one billing cycle and measuring that consumption against the input. But we told them, you move to the next billing cycle and see how your numbers change. The numbers changed by as much as 20-25%. If they're getting 50% with respect to one billing cycle, they were getting 25% with respect to the next billing cycle. And that's a real, it's a real case. I mean, it's not something in theory, and you won't find these in any textbooks. So that's how the NRW creeps in. That's how serious the billing and accounting errors are. And it takes very little effort. It takes very little effort to correct this and to have a proper billing and accounting system. In fact, the apparent losses, the cost of reducing the apparent losses is much less than the cost of reducing real losses. That's why we call apparent losses the low-hanging fruit. It takes very little cost and effort, but the revenue increases dramatically. Let me not say drastically, it increases dramatically. Customer information is not updated regularly. We've seen instances where the customer is either not included in the customer information system, the revenue system. They're totally missing. They have what's called in Delhi a K number, but they're not recorded in the RMS. The meter is being read, but where that reading is going, because it's not appearing in the revenue system, nobody knows. Poorly structured meter or billing systems. This is what happens when you just trust the meter reader to read the meters every time. In the end, he will simply do what is convenient for him and move on. Unauthorized connections. That's a photograph in Delhi, not in some suburb. You see all these plastic pipes going along the road? They're all tapping a transmission main. Transmission main pipes are what bring the water from the treatment plant to the reservoirs. They're not supposed to be any connections on transmission mains. But these are transmitting water, these are tapping that transmission main. Well, they have the benefit of having a 24/7 water system, which nobody else in Delhi has. But it's theft. What are the components of real losses? Real losses, the water which is lost in a water treatment plant by treatment. If you're aware of what water treatment is, a lot of water is lost in clariflocculators, in filters by backwashing, right? That's about, our manual says it should be 5%, but the water lost in treatment plants which are not operated well, it can be as high as 8 or 10%. So your 8 or 10% water gets lost there. Water loss in reservoirs. Most of the systems in India are not maintained well. Operation and maintenance is a serious problem in India. The reservoirs have not been repaired for ages. I mean, the project in which we are working, the reservoirs were built in 1930s, before India's independence. And only cosmetic repairs have been carried out after that. What is the water loss in the reservoir? Nobody can say, because nobody has ever bothered to note it. It's fairly simple to note the water loss in a reservoir. Just stop the input, note the drop in the water level over a period of time. It's that simple. The only thing it requires is effort, but that's not been made.
Any audit is being done by anybody for all these things?
Where?
Can check on all these systems, all these
Where?
things?
Which system?
Wherever the water is coming, anybody is checking, anybody inspecting all these systems?
Which place?
Wherever these waters are coming.
See, if you know, the water is generally under what we call PHEDs or JAL boards, right? They are mostly focused on construction and day-to-day maintenance. That's what I said in the beginning. Non-revenue water reduction, or the concept of NRW, started worldwide around 15-20 years ago. In India, it has caught up only in the past 10 years. Most of the utilities don't have awareness that they have a huge NRW. If you tell them, well, you must have read in the papers, there's a master plan which was done for Delhi by a Japanese JICA-funded study that has quoted DJB's own numbers and said the NRW is 65%. What did the papers say? The papers said that if it was 65%, the roads of Delhi would have been flooded with water. That's the feedback that you get from a common person. Really? Do simple calculation and tell me how that is possible. Because most of the leaks, and that's been found in a project which is going on in Bangalore, most of the leaks, they find their way into the nearest drain or they seep underground. And most of the leaks are very small. And there's so many leaks which are visible leaks. You can go to American Water Works Association website, and there is a drip leakage calculator. Just feed in what is the frequency of a water drop leakage that you would like to test. Feed in that frequency and you'll get a number which says how much water is lost if that leak continues unattended for a week or a year. It's in these ways the water is getting lost. There's so many walls which are leaking. Show me a wall chamber in any city which is not filled with water, and I will put that photograph up on a website and say, oh, this is a fantastic wall. It's that way. I mean, that's how the awareness is not there. The awareness that this leakage should be stopped is not there as yet. It's building up. There are a few projects which have been taken up in India now, but we have a long way to go. The NRW in Tokyo is 2%, in Singapore is 3%. For the cities of India, average of I think 35 to 40%. So we have a long way to go. Okay, coming back to this, water lost in reservoirs, in pipes, valves, even small leaks contribute when they go on unattended for years together. They contribute significantly towards NRW. It doesn't have to be something which is, which erupts and breaks the roads and everything. How do we go about implementing a water loss control program? Phase 1 is to carry out a water audit. Assess the economic optimum volume water loss and fix the performance indicators. Performance indicators in terms of NRW, which we generally quote as a percentage of input volume, is not favored by experts. They generally prefer other performance indicators which are in terms of kiloliters or liters per connection per day. Phase 2 is the pilot study to demonstrate initial recommendations of the water audit analysis in the field. Phase 3 is a global intervention. Once you know where the water is getting lost and how much is getting lost in each component, start addressing those components. Start addressing the component which is the most critical for you, which will bring in the fastest returns with least cost. Phase 4, ongoing maintenance of the loss control mechanism. It's not that once you brought down your NRW to a certain number, it will stay there. It tends to go up again. So water loss control is not a one-time step. It's an ongoing program. It needs continuous monitoring. Okay, this is the start of the water audit. The easier way of doing water audit is a top-down approach. What do we do in top-down approach? First thing we do is measure the system input. It's always best to have a permanent meter there and measure the water input, do a water audit on an annual basis, because water consumption varies. It varies from day to day, it varies from season to season. But if that is not possible, then at least a temporary flow measurement, 7 days, 30 days, whatever you can afford, by ultrasonic portable meters. If that is not possible, then a reservoir drop test. If the reservoir is the element which is giving your system input, then reservoir drop test will tell you how much volume has been fed. Otherwise, the pump curves. Now this was the general way in which we used to calculate our system input. What is the capacity of the pump? Kitne ghante chala? Okay, multiply and we got a system input. That is a crazy way of doing it. You can get an error of almost plus minus 40%, because pumps rarely work at their design point. If a pump is designed for a 40 meter head, you will find it's working at 20 to 25 meter head, because designers always tend to overestimate, be over safe. So naturally the water which it is pumping at 20-25 meters head will be much different from the water which it would pump at 40 meter head. Multiply that by the hours of supply and you will get a humongous error. The next step is to determine billed metered, billed unmetered consumption and unbilled metered consumption. This can be got directly from the utilities revenue system. If the billing has been done, billed metered and billed unmetered. Now what do we mean by these terms? Billed metered, we all understand. Sabke ghar mein bill aata hoga, right? Billed unmetered, there's certain connections which are even now billed at a flat rate, irrespective of what they consume. 15 KL or 20 KL is generally the norm in Delhi. So a connection could be paying for 20 KL, whereas they might be consuming much less than that. And that is what we have found in our studies. The average consumption is much less than 20 KL, but people are still paying at 20 KL. And that is why some of the NRW numbers were coming out negative. unbilled unmetered consumption. Oh, sorry, unbilled metered consumption. In Indian perspective, that is the tanker supply. Now it is metered. It was not metered earlier, but it's being metered now because the utilities are now keen to carry out water audits. But this tanker supply is free. All of you must have availed of that facility in the past week. So that is one example of unbilled metered consumption. Estimate the unbilled unmetered consumption. This component is not very common in India, but in the European countries and in US, the water which is used to maintain the fire system for fire hydrants, more often than not, it's not metered, and of course it's not billed. So this component, if it's there in your system, estimate that. This will be an estimate. Calculate the water loss. The new water loss is simply the system input minus all these components added together, because that is the authorized consumption. Right? So there are some components like the system input which can be metered, and there are some components which will be at best an estimate. You won't get a very accurate figure of NRW with this, but for each reading what we do is we put the confidence limits, an error percentage which we think would be relevant to that component. If your system input was measured by a meter which is not calibrated for the past, let's say 4 or 5 years, then put a range of plus minus 6 or 7%. That's your confidence limit for the system input volume, right? So in the end, we'll get a range, that this is the range in which our NRW can stand. Once we have the water losses, the next thing we do is start assessing the apparent losses. Unauthorized consumption, illegal use, meters not read by meter readers, bypass meters. Now, if somebody is asked to do this at the scale of a city like Delhi, it's nearly impossible. But it can be done for smaller zones, for let's say one UGR or a part of that UGR command area, right? Customer metering inaccuracies, as I showed you the chart earlier. Let's see, did I put that slide? Yeah. This, I had showed you the chart earlier for bulk meter. This is the chart for customer meter. If the customer meter is not sized accurately, properly, then you see this curve which is dipping down. That's the error which creeps in when the water flow through the meter is very less. The meters, consumer meters, mostly under register, and we still complain that our bill is too high. So this is the how the meter accuracies or inaccuracies can be estimated. Theoretically, what we do generally when we carry out DMA analysis is that we take samples of meters, age-wise, brand-wise, and we take a representative sample and we test those meters for inaccuracies. The meters can be tested by putting a calibrated meter in series, by testing in a test rig, or by simply collecting the volume of water which passes through it, weigh it, and you know the volume of water. Simplest way of doing it. So that is how you can note your customer metering inaccuracies. Data handling errors again will be an estimate. And what are we trying to do by doing all this? Once we get the number of apparent loss estimate, we will know the real loss. So why not measure the real loss directly? Because that is the toughest part of this chart. How will you measure the loss which is occurring in through every leak of your system? It's the toughest part of this chart is to measure the real loss through your distribution system. The losses in the treatment plant can be measured easily, and they're being done by all good utilities nowadays. You have input meters, you have output meters, so you know how much water is getting lost in the treatment plant. For the reservoirs, you can estimate, you know the input, and if you have meters at the outlet of the reservoirs, you can measure the loss. But generally the effort is to find the source of the loss in reservoir and plug it, because reservoirs shouldn't have any loss basically. But how do you measure the losses in the distribution system? It's not possible. It's the toughest thing to do. That's why we have this top-down approach, estimate the apparent losses and then estimate the real loss. This is a chart which depicts the results of a water audit. Each component is given in meter cube per day, and each component has an attached error range with it, so that you know how accurate your NRW number is. In this chart, if you see what is the highest component is the customer meter inaccuracies. Very, very easy for this utility to bring down its NRW. It can do a customer meter sample testing and see which meters are to be replaced. So this is a low-hanging fruit. Okay, once we know each component and we want to address them, how do we bring down the NRW? The apparent losses, this again is a chart which is given by IWA. This is a four-pronged strategy to bring down your apparent losses. Unauthorized consumption, that has to be addressed. Data reading errors, customer meter inaccuracy, and data analysis errors. Customer meter inaccuracies can be brought down, as I said, by changing the customer meters. How do you know which customer meters to address? The best way to go about this is to have a GIS map of your system and to mark your customer information on that GIS map. If you have that, then you, by each meter reader is given a certain area. So you can, by meter reader area, you can see which area has the most meters which are not working. First of all, let's address the meters which are not working at all. Take them out, install new ones. Then average consumption. If the average consumption of an area is known and you know, you can see a certain customer who's consuming much less than the average consumption, first thing to go is to check their meter. Right? The first thing to go and check is whether they're at home or not. But the next thing to check is to whether the meter is accurate or not. If it's not, replace it. So it's taken that way, step by step. How to eliminate the human errors in meter reading? There are several systems now which are available for this. They are handheld units. You might be seeing handheld units in your colonies because DJB is putting that initiative in. It's simply the kind of handheld unit you've seen traffic cops use. They will come, take a reading, punch in the numbers and give you a receipt there itself. So that eliminates human error to a certain extent. Again, GIS helps. Sorry, again, I'm assuming everybody here knows what GIS is. Fine, great. So again, GIS helps. Okay, that's a bit advanced. Let's leave it out for now. Right sizing of customer meters, according to this chart, is very, very important. How do you know what size of customer meters to use? The upper chart shows the consumption of a customer recorded by a temporary meter which is put on that connection. This is the diurnal variation. Your meter should be sized such that the average flow which occurs for the major part of the day should be measured through the meter. It should not be oversized. As I said, customer meters generally under register. If they are oversized, it won't measure majority of the flow which flows through it. Control unauthorized consumption, easier said than done, but it's very necessary. This is another modern system which is helping utilities to eliminate meter reading errors and human errors in data transfer. It's called an AMR system, automatic meter reading system. There are some AMR meters installed in Delhi. I don't know anybody here is living in such a colony. What this meter has is it's got a SIM card which reads the volume of water which is passing through the meter and transmits it through GSM or GPRS network. Basically, that's a mobile network directly to the utilities revenue system. You can configure it to read every minute, every hour, once a day, once a month. In advanced utilities, this is also used to get an actual consumption pattern, because whatever diurnal variation we talk about are mostly theoretical curves in India at least. But if you have this kind of meters and you take a reading every hour, you can get a good consumption pattern. Reduction of real losses, again this is chart by IWA. These three charts, the water audit chart and the reduction of real and apparent losses, these three charts basically govern the NRW reduction studies. Real losses, how do you address them? Pressure management, if the pressure in your system is high. Generally that's not the case in India because we don't have 24/7 systems, we have intermittent systems, and again the pressure is not very high. Speed and quality of repairs, the faster you find a leak and plug it, the less your loss will be. And active leakage control. Active leakage control is a concept that you don't wait for the leaks to appear and then plug them. You carry out a leak detection exercise, find the leaks and plug them. And of course, asset management. Let's deal with them one by one. Real losses, again GIS comes in very handy. If you've got the network on a GIS map, you can carry out hydraulic modeling, and there are softwares now which will give you the NRW for that area if you feed in the system input and the consumption, customer consumption. Basically the best tool for real loss reduction is DMA, redesigning your distribution system into DMAs. Are you aware of the DMA concept? No. Okay, DMA is simply redesigning your entire distribution system into smaller areas. DMA is district meter area, it's a hydraulically discrete area. It's an area where you can measure the water which is coming into the area and the water which is going out of the area if there is an outflow. So you know basically how much water is coming into that small area. DMA is usually made for something like 500 to 3000 connections. So it could be one locality. One locality could be divided into two DMAs, or you could have two localities together with the DMAs. It's going down to the micro scale. Putting in bulk meters at the inlet and outlet of DMAs. There is a project going on. There are two projects, in fact, two big projects going on in Delhi nowadays, where they are forming DMAs. So you can talk to your university, maybe they can tie up with those projects going through Delhi Jal Board, and you can see the DMA activities which are going on. Right, one project is in Nangloi, that's quite far, being executed by the Nangloi water scheme, which is an SPV of Veolia and another partner. And there's one which is going on in the Malviya Nagar UGR command area. So basically there they are doing this effort, they are redesigning their distribution system into DMAs. Okay, once you have the system input into that DMA and you know how much water is going out, then the next thing is to take the customer meter, the revenue management readings and find out your NRW. Go again the straight way, what we saw in that, carry out a water audit for that DMA and find out where the losses are. Address the apparent losses, what you have left is the real losses. Then how are real losses located? By leak detection. What you're basically doing is breaking down a bigger problem into smaller problems which can be addressed quickly. And once you have a baseline NRW for each DMA, there will be certain DMAs where the NRW is only 10%, there's some where it will be as high as 50%. So you know, if you address those DMAs where the NRW is high, you can get a faster return. Right? So that's the concept of a DMA. This is a huge topic in itself. There are several books and several projects and several conferences held just around this DMA concept. But these are the basic principles. Minimum night flow analysis. Now, I had talked about water audit, the top-down approach being easier. Why? Because this is the bottom-up approach. The night flow analysis. What is a night flow? In a system which is running 24/7, the water which is going into the system during night when consumption is minimum is nothing but your real loss. It's a leakage to the system. So once you know what is the water going into your this is basically carried out at DMA level, so that's how I'll be talking about it. Once you know how much water is going into the DMA at night, you estimate the consumption, night time consumption, because there might be some restaurants, some hospitals there. So what basically we do is we go talk to the customers and say, a person will be sitting here between 12 and 4, please allow him to take the meter readings. So for bulk consumers, you note down the actual meter readings. For the other domestic consumers, there are certain assumptions which we can make based on the data, global data, and estimate, okay, this is going to be the domestic consumption. So we know that, subtract that from the night flow, and you have your real losses. So that's how we catch hold of the real losses, which, as I said earlier, is the most difficult component of water audit to measure. This is the most accurate way of measuring the real losses. But unfortunately, it cannot be done in India because we don't have a 24/7 system. So we basically adopt a top-down approach. Once you know your real losses, the next thing is to find out where they are. Leakage through a system can be measured by several equipment which are available, and all of them basically are based on the principle of leaks making noise, sound. So they are acoustic based systems. Listening stick, ground microphones, leak noise correlators, noise loggers. Step test is the only one which is not an acoustic, which is not measured by equipment. It is basically subdividing your DMAs into smaller DMAs, closing the walls and seeing which part leaks the most. So that's called a step test. Broadly, that's the concept. Again, leak detection is a whole topic in itself. So this is just introducing it. Pressure control. This graph shows how the leakages vary with pressure. They can vary as much as cubic meters depending upon as cube of pressure. So the best way of bringing down your leakage is to control the pressure in the system. In India, again, that's not a problem because we don't have continuous supply and we don't have high pressures. But worldwide, the pressures at which the water is supplied are as high as 40 meters. There, this is a serious topic. The graph that you see on the left shows the variation of demand, not for an entire day, but for the night time. The yellow part that you see, okay, let me try this. This is the potential saving if you bring down your pressure. This chart shows the actual pattern of diurnal variation which is found globally. The first peak is morning, then it goes down in the afternoon, there's a peak in the evening, and the nighttime consumption is very low. So this is almost same throughout the world. The only difference is the peaks sometimes are 1.5 times the average and sometimes they're twice or sometimes thrice the average. Our manual recommends values from 2 to 3 generally, which is on the higher side for a continuous system. What the pressure management does is it puts a pressure reducing wall at the DMA inlet, and this pressure is brought down to this at the critical point. You must be knowing that each distribution system is designed to have a certain residual pressure at the critical point. That's the minimum pressure that you have to ensure to the consumers. Now, if we have to, at the critical point, we have to ensure, let's say, 17 meters, then the average pressure in a DMA which is nearer to the source could be as high as 25 meters. So you can put in a pressure reducing wall there and bring down the pressure for that DMA. That is a very, very effective way of bringing down the leakages in a system. If you just go on the net and type out pressure reduction for leakage reduction, you will get umpteen number of articles and conference proceedings which you can read through. A lot of case studies. Excuse me. Last one is the asset management. What is asset management? Again, this is an entire topic in itself. The real loss reduction strategies are, they have developed very fast over the past 10 years. And each strategy can be, there are several books on each strategy, right? So asset management is a topic in itself. It's something which is just starting to pick up in India. What an asset management program does is it maps out all the assets, whether it's a treatment plant, a reservoir, a pipeline, sewer, pumps, mechanical components. It feeds in the age of each asset, the cost of each asset. There are certain depreciation values which we take for the cost of each asset depending upon your age, depending upon the age of the asset. And this program will tell you when that asset needs to be repaired or replaced. Basically something that you do for your car. You bought it at a certain price, the value is getting depreciated every year. So after 10 years, you know, resale value will be only this much. Where do you want to sell it? Do you want to sell it when it hits a minimum price, or you want to sell it when it hits a certain price below which you don't want to accept it? Same with the pipes. This pipe is a sample which is taken from the distribution system in the study that we are carrying out. So that's the pipes through which your water flows before it reaches your house, and that's why you have to install RO filters. It should have been replaced a long time ago, only nobody knew that it has to be replaced because it's not mapped out anywhere. The information is in the heads of some linemen. The senior managers don't know. But what an asset management program does is to record all this and to map out a chart. Okay, in this area the pipes are now more than 30 years old. Please replace them. That's basically an asset management program. If you replace your pipes in time before they burst or before they're old enough to leak extensively, you can bring down your NRW. Basically, that's it. Thanks for your attention. Any questions?